And so now I'd like to introduce our wonderful panelists who will be sharing their water wisdom with us today. We have Andrew Schwartz, Brad Coffey, and Tom Painter. So Andrew Schwartz is the lead scientist and station manager of the University of California, Berkeley Central Sierra Snow Laboratory. His research focuses on developing a better understanding of snowfall and snowpack physical processes and the impact of climate change on those processes. Particular focuses of Andrew's research are the impacts of wildfire and rain on snow events on snowpack and water storage. He enjoys teaching a wide range of courses on meteorology, climatology, hydrology, and broader global environmental change. He is a proponent and active participant in science communication and believes that sharing research and science with the broader community is beneficial to all those involved and results in better science-informed policy. Tom Painter, on the end, is the founder and CEO of Airborne Snow Observatories, Inc. As a snow hydrologist and remote sensing specialist, he was recruited to the Jet Propulsion Laboratory in 2010 to create what became the NASA Airborne Snow Observatory. In 2018, he was awarded the NASA Exceptional Technology Achievement Medal and the Bureau of Reclamation's John W. Keyes Award, both for his team's work on ASO. In 2019, Tom was elected as a fellow of the American Geophysical Union. In 2019, he departed NASA JPL to pursue the technology transfer of ASO to the operational commercial world to make true the vision of providing quantitative snow measurements and accurate snowmelt runoff forecasting around planet Earth. And last but not least, Brad Coffey is the water resource manager for the Metropolitan Water District of Southern California. In this role, he's responsible for planning and managing Metropolitan's imported and local water resource programs, advancing water use efficiency, and providing supply and demand forecasts for the region. Brad joined Metropolitan in 1990 as an assistant engineer, and he previously served as assistant group manager for Metropolitan's water systems operations, where he helped manage more than 900 employees who import, treat, and deliver water through Southern California. A registered professional engineer in California, Brad earned degrees in mechanical and environmental engineering from Virginia Tech, go Hokies, and holds a master's degree in public administration from USC. I can't say go Trojans though, because we're at Stanford today. So Andrew, I believe you're gonna start us off, and if the other panelists, you can take a seat in the audience if you'd like to view each other's presentation, and so we'll have you come up. So yeah, pass it off to you.
Good morning, everyone. First, I want to say thank you to all of the previous panelists and the organizers for the summit. It's been great. And Lindsay, thank you for organizing this panel as well. So my name is Andrew Schwartz. I've been the lab director up at the Central Sierra Snow Lab for 2.5 years. Before that, I spent my time about 4 years in Australia doing research on how wildfire burn scars affect our snowpack and water resources there. So we're going to start with something that I'm sure everyone was looking really forward to today, and that's late 1800s notable history, okay? That's all what we were expecting, right? So this man here, I'm sure some of you recognize this photo, maybe. This is Thomas Edison with his invention of the phonograph. This was patented in 1878, okay? Actually, a lot of the work that was done on this was not too far from here. The same year, the first telephone switch room was installed in San Francisco. It serviced a whopping 18 lines, and there were still a lot of people that were very hesitant about whether or not this new telephone technology would take off at the time. A little bit closer to home with weather and water, in the United Kingdom, the same year, 1878, we started issuing our first weather maps, or they did, I wasn't part of it. And this isn't exactly what they were issuing because this is a few years later, but it would have been similar to this. 1878 was a big year. Now, to bring it a little bit closer to home, this is the Transcontinental Railroad. It was not completed in 1878, but about 20 years prior. The reason why we're interested in 1878 is because that is the first year that the railroad did something very unique and very important to us in the water world. They gave us our first recordings of snowfall and snowpack depth on Donner Summit. Almost 150 years ago, something that we've continued through to today, although this chart is not updated. And this is, as far as we're aware, the longest standing record in the world, okay? Very important. Oh, it is advancing without me. That's okay. So that was 1878. After the turn of the century, this man here, Dr. James E. Church, who was a professor of literary classics at the University of Nevada, Reno, became enamored and developed a snow measurement tool. But he became enamored with the hydrology, particularly snow around the Tahoe region, and he developed what is on the top right there and what is known as the Mount Rose Sampler. Well, now it's called the Federal Sampler, but the same thing. The interesting thing about this was it was developed in around 1906, depending on the literature that you're reading. But we still use it to this very day. That image on the bottom right is what we were using, my team, back in April when we were doing the Onion Creek Snow Survey, okay? Over 100-year-old piece of technology that we're still using to determine our water resources today. So that was the turn of the century. Come middle of the 20th century, the Snow Lab opened. This was in 1946. We took over those wonderful records that the railroad had started on Donner Pass, and we have continued to develop that into becoming one of the longest records, or excuse me, the longest record in the world of snowfall and maximum snow depth. And that allows us to do all kinds of cool things like look at, of course, trends in that, our variability, what's happening with climate change. And we see a lot of things like shifts to rain from snowfall, right? That data set helps us find that. The Snow Lab has also taken a significant role in developing new technologies and been a piece of all these new technologies as they've been developed. It's been a wonderful place to have these things tested and compared to each other and validated against each other. So we have the Mount Rose Sampler up there on the top left. That's our over 100-year-old piece of equipment. The image in the middle on the top, those are known as snow pillows. And if you're not familiar with them, they weigh the weight of the snow to get the amount of water in it. And we're really concerned here about the depth of the snow, the density of the snow, and the snow water equivalent, right? That makes our world go round. That's what we call our mass balance. It's water in, water out, right? On the far right on top, we have Randall Osterhuber, who was my predecessor at the Snow Lab, standing next to a fluidless snow pillow. Again, very interested in how much water is in the snowpack, because of course that helps you all make your decisions on how much you have to distribute, and we can plan around how much we have in the mountains. On the bottom there, we have kind of a history and timeline of snow depth measurement. Ruler, which is exactly what the railroad was doing back in 1878. We still do that every time it snows at the Snow Lab. We do daily amounts. We trudge out there 8 a.m. and 4 p.m., stick it in there, and guess what? That is still our most important measurement. The Weather Prediction Center out in Maryland uses that on a regular basis to coordinate and calibrate their weather models. Ruler is still very important. Next to that is what is known as a Judd sonic snow depth sensor, which emits a pulse of sound, it bounces off the snowpack, comes back, and based on the speed of sound, we can tell how far away that snowpack is for the sensor, and therefore how deep it is. On the far right, and I'm sorry, Tom, I stole a picture of your beautiful plane, but is Tom Painter's Airborne Snow Observatory, or one of the planes, now that the fleet is growing. And that is the newest way to really determine our snowpack over a wide area. That is incredibly useful because we get variability over that area. We can better calculate how much snow is in catchments instead of at a single point. So that's our mass balance. Ignore the equation on the bottom. I stole this from a lecture from Berkeley. I apologize. The picture is the important bit. So that's only half of the story, right? We also have to take into consideration what we call our energy balance. How much energy is going into that snow? That's going to affect our timing. When's it going to run off into those reservoirs? Is it going to be fast? Is it going to be slow? When are our peaks going to occur? So this image shows a number of different things. First, of course, the sun driving melt of the snowpack. That's the most important one. Our solar radiation drives the most melt. We also have the QH and QE, which is just what we call heat fluxes, sensible heat flux, latent heat flux. And that's just heat going to and from the snowpack with wind, okay? So we have that, and then of course at the bottom we have our soil heat flux as well. The ground actually does melt our snow too. Now the important part about this is we've made big strides in this area, not necessarily going back 150 years because we didn't have measurements of energy back then, but in the recent decades we've come a long way in our energy balance measurements. And these are vitally important to figuring out how we can improve our models, how we can feed information into our models. And so these are just a few instruments that we use to help measure that. And all of these play a very important role. They're not necessarily at every site that we monitor the snowpack at, but some of them, or a lot of them. We do have radiation measurements out a lot. We do have, of course, temperature and relative humidity. These are all very important and have come a long way in the history of snow and water and weather. So when we bring together these developments in energy balance, these developments in mass balance, we get to things now where we can have really important decision support tools that are supported by the new data that's collected by these important instruments. This is from a paper, Hagley et al., 2022. Anne was the primary author. I was a co-author on this paper. We effectively looked at rain on snow events. And I don't know if you're familiar with these, but there's really one of two things that can happen with rain on snow. Either one, it percolates through the snow and goes into your streams, you get discharge and you have inflows into your reservoirs. You'll see a peak, but nothing too crazy. The second possibility is we can see a lot of melt of that snowpack along with the rain on top of it that can cause catastrophic flooding. This has happened a number of times, including in Reno, periods where the city's been under feet of water. So having these types of tools that are based on the measurements that have come as far as we have is incredibly important, because we can say, here's this decision support tool, here's the data we're seeing. Do we need to release water to make room for all of this additional flood that could be coming in? Or can we kind of keep our reservoir releases calm and bring those reservoir levels up using only the precipitation that's falling, right? So snowpack decision support tools, incredibly important, and realistically have come a long way because of how far our observations and measurements have come. Now, this is from, the image on the right is from M3 Works, who works very closely with Tom Painter's group at ASO as well. And this is a model output, which shows basically the change in snow water equivalent, the amount of water in the snowpack in the top left, and then the snow water equivalent overall in the bottom left, and then on the right, how that's distributed over the elevation bands. All of those energy balance measurements, all of those mass balance measurements can be brought together to help put this model data out over an entire catchment so we have better ideas of where this water sits. And we can get better forecasts potentially seasonally based off of that. So when we look at this, it helps us get away from one of the things that we developed when we have this long record, right? We have 150 years of water. When we look at that snowfall chart, and from that time that began, we started saying, okay, we need averages. We need averages. What can we expect on an average year? And I think after this last year especially, we're well aware that average years really don't exist a whole lot. And so when we are now moving forward with these models, with these decision-making tools, that helps us take all the information that's available now and bring it into a forecast that is for this month, this year, this season, and today. And that's a lot different than what it used to be, where it's, here's the maximum amount of snowfall, maybe we'll get that next year, you know? So it's really helping us expand into the future with climate change as well. And I think this is my last slide. But the other thing here too is we're getting what is known as compound events, right? With climate change, our wildfires are getting larger. I don't think that's any surprise to anybody in here. And realistically speaking, every single one of those fires that occurs in an area where snow happens, this 2 images from the Caldor fire, that's going to fundamentally alter the way that area melts. It's going to fundamentally alter how much water is coming out of it, the timing of that water, and the quality of that water. So these new tools that we're developing in terms of observation, measurement, they're helping us figure that out as well. So that's my short spiel on how far we've come over the last 150 years or so and how it's leading into today's advancements. To talk more about today's advancements and how we use that data, I'm going to bring up Tom Painter.
Just give my time to Andrew to keep going. There wasn't enough time for 150 years worth. All right. Well, thanks for inviting me and including me in a great panel. And I really wish that we could have a couple of days to go through this. But we actually are doing such a thing next week. We have the ASO workshop in Mammoth Lakes. It's not too late to register and show up or get online. And that'll be 5 days. It'll be Monday afternoon through Friday. And you can find that at airborne-snowobservatories.com. And if you miss it this year, be sure to come next year. All right, so obviously we are really pushing on technology, and that's much of the reason for the California Water Data Organization and the summit. And we are at such a crossroads right now in terms of the hydrologic cycle, in terms of population growth, and the absolute demand on each acre foot or even gallon of water, and it's pushing us into new places as well. Arizona limiting construction around Phoenix as its water supply dwindles. That was in science fiction a long ways off back when we were starting our careers, and now we're getting there. But a thing to remember that's really important for this session is that snowpack represents about 70 to 80% of the annual precipitation that falls onto the West and in particular in California. And the reason I like to highlight that is that often you'll see that water usage in California, about 30 to 40% of it comes from snowpack. Well, what gives with that? Well, what gives is what we make up from groundwater pumping, and so we are tapping into that long-term supply. But what really gives us our main water supply and the replenishment of groundwater is the snowpack. The forecasting, as Andrew was saying, goes back to this long history, and sites such as the Central Sierra Snow Lab and Donner Summit give us such an amazing ability to understand what the hydrologic cycle does and what it is now doing. Unfortunately, we now live in a time of we're leaving the linear part of climate change and we're moving into the nonlinear part of climate change, which is carrying us then into much greater variability in the hydrologic cycle. And we see that in the records, not only from Donner, but from the Tuolumne and various parts of the Sierra Nevada, that we're starting to see a wilder and wilder runoff hydrograph and water supply. And our ability to forecast that, relying on history, is increasingly challenged. And you can see down here in the lower left, these are just DWR's B120 forecasts versus the California Nevada River Forecast Center forecasts. Sometimes they're aligned well, sometimes they're wildly different, sometimes they have enormous ranges against a much narrower range. And I think many of you are familiar with the results of the audit, and I'm going to come to that in my last slide. Some of the percentage differences. This is from the Rio Grande in Colorado. Those numbers, the big blue and the big red, those represent enormous tension on the water system and ultimately on people. So averaged, though, over that time, it's about zero, all right? But people don't live averaged over 20 years, right? We live moment to moment. We live right here. We live within a season. So intra-seasonal forecasts are incredibly important. And so we need to move away from just getting it right averaged over 10, 20, 30 years. We have to get it right today for this season that we're in. So as Lindsay mentioned, I came from NASA. I was a NASA scientist for almost 10 years, and I was brought there to build the Airborne Snow Observatory and then ultimately to carry that to space. Well, what we found in the process is that a spaceborne version of this is not going to work out. What's required for the technology from space doesn't work well with the physics of snowpack. And so airborne LiDAR and the modeling that we do turns out to be the best way to do that. And that's why I ultimately decided to leave NASA and become a businessman in a public benefit corporation. But during that time that I was at NASA, we had the Global Precipitation Measurement Program to address rainfall, ASO, of course, to address snowfall, groundwater coming from the GRACE mission and then the GRACE follow-on mission, SMAP for soil moisture, and then EcoStress came along, flying on the International Space Station, and that was to address evapotranspiration. There's another mission that's coming along called SBG that's likely to carry a thermal imager. And then also there's the Open ET program that my colleague Forrest Melton at Monterey and he's also at NASA headquarters initiated and has really been carrying forward to take advantage of the various available satellite data sets. And then very recently, the SWAT mission, the surface water ocean topography. Sorry, they changed the name from what it originally was when we were looking at this back in 1997. And then back to observation and forecasting and runoff ASO. So where are we now? Well, and where are we headed in terms of embedded infrastructure? Those missions go away ultimately, all right? Those are research missions and not operational workhorse satellite programs. And so where we're left is with the ASO and then Open ET. And so it's critical that we continue to push towards being able to have those understandings and the operational measurements. All right, so finally to the Airborne Snow Observatory. So we started in 2010. We had our first flights in 2013, and I'll go through that in a second. But what we're after are the two most critical snow properties, the snow water equivalent and the snow albedo, the snow reflectivity. And the reason, obviously, for snow water equivalent is we want to know how much mass there is. The reason we want the snow reflectivity is that about 90 to 95% of the energy that goes to melting snow comes from absorbed sunlight. And snow is, as my graduate advisor likes to put it, the most colorful substance on the planet. You just can't see it with human eyes. You have to go out into the near infrared and the shortwave infrared. And so that's what we do. So, all right. Is the top button is not a laser pointer, or is it? I'll throw things at the screen. All right. At any rate, over here, what we're showing in this Wile E. Coyote type figure is the scanning LiDAR, which is measuring the topography of the snow surface. We will have measured it before when there's no snow on the ground. Yeah, I won't push it. And the difference between those two gives us the snow depth. Right behind it is the measurement from the imaging spectrometer, which is measuring reflected sunlight in hundreds of wavelengths, about 588 wavelengths of light. And those actually look like that. So snow water equivalent comes from that LiDAR elevation, the snow depth comes from the LiDAR elevation, and then we couple it with observations such as Andrew's, and our model density, which is the iSnowbow model that he was showing from our colleagues at M3 Works. And those combined in a map form give us a spatial distribution of snow water equivalent at 50-meter resolution across water equivalent across that 50-meter pixel is less than a centimeter. And that comes from the averaging of these 3-meter pixels that we start with. So it's a remarkably accurate measurement of snow water equivalent. And then behind, so this is the LiDAR right here. Right behind it are the imaging spectrometers, which go visible through shortwave infrared, and they give us the albedo, but also the surface properties of the vegetation. So being able to understand the how snow grain size changes, how impurities in snow are impacting the snowmelt rates. So we get dust. We also are getting a lot of black carbon deposited out onto the snowpack from the Caldor fire and the Dixie fire. And that's having enormous impacts, as I'll show in a second. Then we have the physical modeling through the ice snowbow model. And then we're carrying the snowmelt into runoff through the wharf hydro model, which is at the core of the National Water Model, but it is a far more sophisticated model than just the National Water Model. So that is becoming our hydrologic modeling framework. Our operations are, we go up and we fly, just kind of like when you're mowing Fenway Park or Candlestick Park, which doesn't exist anymore, is that right? But then we piece that back together into an image. And we have rapid product turnaround. We get the products, we pull about a terabyte of data off of the plane every time we fly, and we crunch those data down. And within 48 hours, we've produced a snow water equivalent map, a snow albedo map, and it's been integrated into the model. So this was an enormous challenge, and it was really important for us to be at NASA to be able to do that. Here's the wharf hydro modeling system, and this is now being implemented by the state of California through our program. This is becoming the answer to the results of the audit. So I'll come back to that here in a second. All right, I just want to show you some of the results. So this is from the Kings, looking up the main canyon in April of 2022. Here we are in January. Snow depth down here. Notice how many cells are in the 5+ meter range. You can't see it, can you? You really want to get up and see it. I'll send you the slides. At any rate, and many of these places are 10+ meters, and even some that we measured on the backside of Mammoth Mountain over in the Minarets were on the order of 25 meters of snowpack. So some places over 100 feet of snow. Another shot in the Kings, same time frame. So as Andrew indicated, we are able to get the comprehensive measurement. So instead of a handful of measurements at detailed long-term sampling sites, such as the snow pillows and the snow courses, instead we get a snapshot that is the comprehensive picture across the basin. Now, are these disjoint from one another? No, absolutely not. It's critical that we have those measurements. Those are ideal in giving us an understanding of the snow water equivalent at a point, the snow density at a point. That allows us to update our models. And so these really complement each other enormously well. And so important are those old measurements that we are establishing within ASO a program to go out and make more measurements. So with the federal samplers, the Mount Rose samplers, to really add to the density of those measurements across the landscape. Then looking at the snow albedo, this is the San Joaquin Basin in mid-April, and the fire scar from the Creek Fire is highlighted here. And you can see what's happened to the snow reflectivity, all right? You really want to you want snow to be up there in the white. You want it to be up around 85%, 90% in snow reflectivity. But instead, in the fire scar area, what we're looking at is all the black carbon that has sloughed off onto the snow and drawn it down into the 50, 60% range, right? What that means then is that the absorbed sunlight has gone from 10 to 20% up to 40 to 50%. Right? Well, already remember that the absorbed solar radiation is what drives snowmelt. So wherever we're having those huge wildfires, we're driving massive melt now and losing that snowpack. I think the final for imagery here is just looking at Mammoth Mountain ski area. This was from funding from the Office of Emergency Services for the east side. And there's the snow depth data. Again, some of these places are on the order of 18 to 20 meters deep, and they're still holding snow today. In fact, out on a hike this last week, I was at 9,000 feet and I was still stepping across snowpack. So it was a big year. All right, so the program, we started our first flights in 2012, and then we just started seeing a lot of growth. The state of California was a partner of ours from the very beginning. And then we started adding support from the state of Colorado. And I think this blue line should actually be below Southern Sierra Nevada extension, but we saw that growth. And then in 2019 is when we made the transition to being Airborne Snow Observatories, which is a public benefit corporation. And then we've just grown like crazy from there. And actually off the bottom here, I think this is a Mac to PC issue, is just the extension. So we've moved from a single plane, and now this year we'll be moving up to 4 aircraft. And then in the coming years, moving to many, many more. The results here, so in the upper left corner, this is reservoir operations. This is from Hetch Hetchy. And what you see in this figure is Hetch Hetchy inflows versus MLR estimate is essentially ASO snowpack guided by some precipitation. But it shows you an absurdly high R squared. And as we keep adding points through the years, those keep falling on that line. And that's what allows Hetch Hetchy and other basins to really be active now. When they get a measurement in the middle of April or in March, they know how much water they're going to have for that seasonal flow as a minimum. Of course, there can always be precipitation that comes afterwards, but they know at a bare minimum, and therefore they can start getting very aggressive with operations. We've got the proactive flood management from 2019 in the Kings. They were able to save about 100,000 acre feet of water in their operating district. And at that time, about $100 million worth. There are the ecological implications. This is in the San Joaquin with the river restoration program for salmon. And then the reservoir operations timing and the hydroelectric generation. We're also working with the river forecast centers. This is a result from the Colorado Basin River Forecast Center. The experimental forecast in these cyan circles, that represents the update of the model with the ASO data, whereas the regular span is coming from the model without ASO, and it just shows that that's nailing the forecast very well. Then over to the right are the WRF hydro results, and this is an ensemble of forecasts with the median represented by the white bar in the middle. Both of these are in the absence of ASO. Black represents the observed, and I forgot to mention this, but I'll come back to it. But here we then see the median forecast with the ASO update hide behind the observed. So it turns out that having really accurate snowpack information, snow water equivalent in the snow albedo, is key to an accurate forecast in these kinds of basins. The other thing that I had wanted to mention here is just that the forecast error that we're seeing from the river forecast centers is really related to the snowpack error. Obviously, there's some scatter in that, so it's not uniquely responsible for it, but there's a pretty strong relationship there. Finally, the adaptation in practice in the feather, and you can see the Dixie Fire perimeter there in the dark patch in 2022. So remember, in 2021, that was when the fiasco happened at Oroville and the State Water Project, and we weren't yet flying the feather. It was actually that event that precipitated us flying the feather as an extension among other basins that were added. But similarly, in 2022, we had our first flight in the middle of February, and at that time, various forecasts were indicating a non-trivial snowpack and non-trivial runoff. And we had our first flight, and I had to call Dave Rosardo at DWR and say, before we sent the results, it's happening again. and just get everybody ready for this because there's a lot less snow than you thought there was. And so we had to draw down all of those forecasts, and many of them take advantage of ASO data. Some of them don't. And you can see those that don't, including the SNODAS and the University of Colorado Boulder product. The other thing that we were seeing was all this impact of the soot from the charred areas and what impact that was having on albedo. All right, so I'll just get to the point. The audit really points to full ASO implementation, and if you read through, you can read where there was a partnership between the state of California, hydrology, and NASA for aerial snow measurements or observations. They don't say ASO explicitly, but that's us in there from our NASA time and then subsequently. And DWR invested in ASO starting in 2013. Frank Gerke was the one that made that happen with us and has done so since. And they have been trying to get the adequate funding for the full program, but have struggled with the process, and that happens. It's the state government, and changing from something that we've been doing for many decades to something brand new like this, it takes time. But the complete program that they've been heading toward is ASO with its physical snowpack modeling, and then the physically based runoff for Morph Hydro, and that's including the ice snowbell model. And you can see all the areas where we have planes. It kind of looks militarily set up, but it's not quite like that. They're very peaceful planes. And we try not to drop anything out of them, although we've been accused of dropping flies into the Central Valley. We get all kinds of questions. At any rate, to be able to deal with climate change, coming back to that, we need to know what's going on with the snowpack today. We need to be able to know how it's changing. We need to be able to have a comprehensive measurement across those basins and then have it physically derived. That way we don't have to rely on the past to have an accurate forecast today for our partners. So I want to say DWR actually has been planning for this and working toward it. It just happened that 2021 happened while they were in that transition period. But fortunately, they're heading towards the complete program, which will carry us all the way from the Kern up to the Trinity, including all of the basins. Right now, we're just at 12. So I'll stop there.
Well, thanks, Andrew and Tom. And I have to let you know that you're two of my scientific heroes. And it's not a long list. And for full disclosure, I bought a Central Sierra Snow Lab t-shirt. And a friend of mine's son works for ASO. ASO t-shirts are available. Okay. So just in case there was any perceived conflict of interest. So I work for Metropolitan Water District of Southern California and help manage our water resources. We serve a population of about 19 million people, which in total use about 3.5 million acre feet per year. Some of you might not be familiar with the unit acre feet, but it is what it sounds like. It's 326,000 gallons, and it can serve 3 Southern California families for a year. So the Southern California uses about, that, as I said, 3.5 million acre feet, and that is what drives the economy of Southern California. If Southern California were a country, it would be larger, its economy would be larger than all but 11 countries of the world. So where do we get our water supply and water sources? The largest is from local water supply. Now that does include some imported supply for the city of Los Angeles through their aqueduct. Groundwater, Southern California is rich in groundwater resources. an increasing amount of water recycling. In the 1980s, only about 0.5% of our water was recycled. By today, it's about 12% of our water is recycled. Desalination is another one. The Western Hemisphere's largest ocean desalination plant is located in Carlsbad. So I'm mostly going to talk about our Northern Sierra watershed and our participation with the State Water Project. State Water Project run by the state of California, but it's paid for by its contractors. We have participation rights in the State Water Project of about half of the production of the State Water Project. That means we pay about half of the costs of the State Water Project. I'm not really going to talk about the Colorado River. I'm not really going to talk about local supplies, but they are all amazingly important for Southern California. So we've seen really large swings in the State Water Project availability. Now, this isn't purely Snowpack. This also includes limits of physical infrastructure. This includes important regulatory, environmental protections. And so, but it probably mirrors that somewhat. The yellow bars are water and precipitation, water that came and was available to us, but we couldn't use. Those big yellow bars in the early part of this, in the late 1990s, is before we had built our Diamond Valley Lake, an 800,000 acre-foot storage facility. Once we had that operational, that helps us take into Southern California the bountiful years. And so you see, in general, the remaining yellow bars, or water that was available that we couldn't capture, has greatly diminished. We can also see how variable this is. At that, our full allocated amount, it's around 2 million acre feet. And that's what we have available to us this year. In 2021 and 2022, it was about 5% of that. So it's about 100 to 200,000 acre feet. Remember, we supply about half the water to Southern California, and Southern California uses about 3.5 million acre feet per year. So if we just get 100,000 acre feet per year, we're really drawing down on our storage. So this is our storage and the end of year balances. And as you see the bars grow, those were periods of wet years. As you see them shrink, they were periods of dry years. And even with this year, we expect to be able to end up at a record amount of water in storage. So many people think water in storage is water behind a dam somewhere. We have water that is stored in Lake Mead through our intentionally created surplus. We have water in our reservoirs like Diamond Valley Lake. We have water with our name in it in State Water Project reservoirs that we can draw down. We have water stored in the Central Valley of Southern California, which we fill and use through a conjunctive use process. And we have water stored within the Southern California Basin groundwater. So it's really a heterogeneous mix of these things, and it's not all single year dependent. So there's been some talk about Lake Oroville Reservoir, and I'll just speak as an agency that pays half of its bill and has paid for half of it. This shows from December of last year, December 2022, through July of this year. And you can see how much the reservoir has grown. This is again reflective of the runoff into the reservoir. And one of the things that causes this is this tension between flood control and water supply. So if we have a prediction of runoff that's higher than it actually ends up, it really hurts agriculture and municipal users, because we have to then scramble to pull from our storage resources when that snow doesn't appear as runoff. On the other side, if you predict amount of runoff and you miss it on the low side, that's a flood risk. So we're always trying to balance this improved water supply and improved flood risk. And we think one of the best opportunities to do that is not build a bigger dam, but is to use what's called forecast-informed reservoir operations. So rather than a reservoir operating criteria that was developed in the 1950s, we would use real-time data to see where an atmospheric river is, and if we would have time to evacuate that space. And this would begin to let us dip into the flood control storage and manage the water better for all purposes. But I'll get to a slide in a minute that FIRO won't really help us that much with. So I'm going to talk about this graph for a bit, but one way of thinking of this is California, through a changing climate, will see less snow and more fire. And as you heard before, more fire means less snow. California's water infrastructure was largely built in the early to mid 1900s based on hydrologic records back to about 1880, when people were starting to think about building reservoirs. And the assumption was what's called stationarity, that the average and the distribution of the years would continue. And so that was what planning was based on. The problem is that we're operating this infrastructure that was dreamed up in the 1880s, was designed and built in the mid 1900s, is being operated now. This probably means I'm running short of time. That's operating now, and that we want to last into the 21st century. The 21st century for me used to feel a long ways away, but if you realize if you hold someone's baby or even a young child, in all likelihood, that person will be alive in 2100. So to me, that really provides a motivation for us to think about what our children or grandchildren will actually be experiencing. So now back to this graph. California will likely have about the same amount of precipitation as the climate changes. However, how it falls and when it runs off will change dramatically. So the top graph shows that the circles are representative of the months and the amount of runoff that occurs in each of those months. And as you can see, this data from 1980 to 2000, the peak runoff month is May. And that is different than the peak precipitation time, which is usually November through March. So what that means is that we have the capability of storing more water without as great of a risk of large storms coming in. So fast forward the time to when your children or grandchildren are here, and though it's the same amount of runoff, what happens is its peak moves almost 4 or 5 months earlier. And in fact, in 2022, the runoff began and the snow began to decline in January. So imagine every year, like January, with the runoff. So that then means you've got a lot of precipitation coming. You need flood control space because of those are the rainy months, and you can't hold that water because of flood protection. So this infrastructure is really challenged in the 22nd century if these runoff patterns persist. This was from work from UCLA. Another factor, and I showed you kind of that high variability, is that scientists expect that to increase to nearly double by the year 2100. That means that the likelihood of having a very dry year followed by a very wet year, its risk or reward has doubled. So this is what we need to be thinking about as we think of our infrastructure moving forward, and what Metropolitan is doing with its new climate adaptation master plan for water. And I'll talk a little bit more about that. So how do we use these data for our operational decisions? Well, we rely on others. We don't want to be climate scientists, as wonderful as that must be. But we want to be smart consumers of the data produced by climate scientists and meteorologists. So we're not into your stuff, but we want to be good consumers. And I ask you to help us be good consumers of this information. So what we do is we take information from the Department of Water Resources, from the California-Nevada River Forecast Center, from NOAA, from our understanding of how the environmental parameters will affect the water flow. And we have some models that we run internally. But it's also a lot of a few of us kind of going into the conference room and arguing about what these data mean. And then we make a decision based on that. And the decision can be really important for Southern California, whether in a year or two, we may have to dramatically cut back the water supply, or whether we're spending money when we don't need to. For example, in 2022, our board authorized our general manager, who's here with us, to spend up to $100 million to purchase water on the transfer market because there was so little water available from the State Water Project system. Now, we didn't have to use that because this year was very bountiful, but that gives you the size of the magnitude. The group I help lead with really talented people that are involved in these decisions. Overall, we spend about $800 million per year. And so we're talking like real water and real money, and so a real interest in the things that you are doing. So what are we looking at in the future? And I talked about what those futures might include. We did an integrated resources plan needs assessment the past year or so, and we looked at 4 different scenarios. And the main axes on those scenarios were left to right, mostly demographic and behavioral. So how quickly Southern California would grow, or how slowly California would grow, how local resources would perform moving into the future. And so on the horizontal, it's just demand on our water, higher or lower. And on the vertical axes, it is regulatory constraints and climate. So in the top row, we use representative concentration pathway 4.5. And a lot of people say RCP 4.5, and we all don't know what it means. Well, what it means, that's a measurement of the effect of carbon dioxide on the atmosphere. And the 4.5 is the reflecting of the energy back to Earth. And 4.5 means 4.5 watts per square meter are reflected back to Earth. In our higher climate change scenarios, we use representative concentration pathway 8.5. And that is nearly a doubling of the reflectance. And that represents a world in which our carbon emissions don't decrease. RCP 4.5 is a world in which our carbon emissions do decrease along the lines of the Paris meetings. So what we're really wanting to do is pre-experience our future and say if, for example, we had high growth, high demand growth in Southern California, and not the worst case, but a worser case for climate change, what do we need to plan for? Not build today, but plan for. And what would we need to watch for in order for us to make those decisions of what to build for? So with this, we've adopted a climate adaptation master plan for water. In our IRP needs assessment, we primarily looked at the percentage of years where we had a shortage and how great that shortage was, or the percent of years that we had a surplus and how great that was. But it didn't have a lot of longitudinal over time information beyond 25 years. We do within 25 years. And this, our climate adaptation master plan, will take that kind of this needs assessment as its backbone, but also lead us to think about the reliability of Southern California's water supply, the resilience, which is basically reliability if something bad goes on, of our water supply, how affordable it is, and how the different scenarios would affect Metropolitan's financial sustainability. So this is where we're in our planning stage. We do both planning and implementation within the group, of the Water Resource Management Group. And I want to acknowledge there's probably 5 or 6 water resource management professionals in here, which tell me what to do. So this is like our experience. What we really want is a scientifically sound, data-based projection of runoff from an urban water supplier's perspective. Not from, and so that's kind of like rehashing this back and forth between flood control and water supply risk. And I know we can do that by working together and learning more of how each other works. And water data is that common denominator that we'll have to share in order for that to happen. So thank you very much.
Well, thank you everyone for coming, and thank you to our panelists. I just want to apologize because we don't have enough time for questions, and it's time for lunch. So that's the good news. But yeah, thank you everyone.